were finite and limited, that's actually I would say the major difference between computer science and mathematics. You have to deal with finite and basically limited resources. And the challenge is not only, as in math, to find a solution to a problem, but to find a solution that is resource efficient and makes use of resources as optimally as possible. And so recycling is our word for today. We want to recycle basically anything, but in particular memory. Now, the subtitle here is why you should care. And again, I'm looking at you as potential compiler writers. Maybe it's a little bit ambitious, but anyway, I'll for the moment, I look at you like that, and if you are a compiler writer, then again, I'll hope to convince you that you should care. Now, 2 slides about my own interests. Very first slide about the overview of the lecture. Basically, it's divided into 4 parts. This just mentioned quick introduction of myself, then the garbage collection basics that should be known by everybody who wants to see at least somehow behind the scenes, and then some advanced topics, and finally a conclusion. Now, in one word, if I would have to characterize my interests in computer science and my achievements, then I would probably summarize it as holistic systems design, in the sense that systems design from the ground up, not assuming that anything is given, not even hardware. Of course, in the earlier times, hardware was very much given. It has changed, but as much as possible, we want in our group, which is called Native Systems Group, by the way, we want to basically design everything from the ground up and have control over all levels. And these are some examples of what we have done. I think the first important step in that direction was our Lilith Modular 2 project, workstation project very long ago. And actually that was basically Niklas Wirth's team that started that project. You may know Niklas Wirth, he's the inventor of Pascal, and he's actually a very renowned guy in Switzerland and all over the world, actually. The incentive for doing this Modular 2 project was to show that you don't have to use machine code or C code to program systems, you program operating systems, but you can use high-level constructs, abstract constructs. So the word there was modular systems programming, and the concrete way of how to do that was using this M code. You may have heard about the P code. The P code was actually the key to the success of Pascal. In the very early times, Pascal was running on Apple II computers. That was the first time when a high-level language was running on a personal computer. And the trick basically was to have this P code in between the high-level programming language and the machine code. The compilation worked in 2 phases. First, the compilation went from the high-level abstraction, high-level language to the P code, which was rather simple because the P code was a virtual machine, basically structured as a stack machine. Basically, all the operations were stack-based. And here we tried to imitate this P code to change it to what's called the M code. And the important step was to microcode it, no longer to implement it as a step in the compilation process, but really to have it as a part of the runtime system, microcoded runtime system. And that gave a very small footprint of the entire system software for that machine. It was one of the first personal workstations in Europe ever. And then there followed other projects like Series Oberon desktop computer, and in the newer times it was the A2 Swiss Industry Controller. And finally, the current project that I'm working in collaboration with Microsoft Research is actually a supercomputer in the pocket, meaning that you bring down supercomputer capabilities to embedded systems by using custom chip design, basically application-aware chip design. So in that last project, compiler construction even includes the chip design level. Okay, so that's the summary of my interests, holistic systems design, recently including the hardware level, actually. Now the basics. Let's come to the actual topic of today, the basics of garbage collection. Now, first of all, we have to be aware of the fact, that a system, a computer system, and I'm very general here, is basically a collection of fabrics, object fabrics. There are a lot of objects, and if I say a lot, then I mean really thousands of objects per second generated every time when one or several applications are running. And of course, these objects have to be allocated in the memory of the computer. And if you don't do anything, then you gradually fill up this memory, And I just quickly checked. I mean, after some 10 hours, if you have, for example, 8 gigabyte main memory, and if you're assuming a sort of medium rate of 1,000 to 8 byte objects per second, then you fill up this 8 gigabyte in about 15 hours. It's still a long time. I mean, these memories have become big. So if you don't do anything, then if your system doesn't have to run beyond 10 hours, 15 hours, then you are safe. That's okay. And there are actually good reasons for that. I mean, because allocation of memory is very simple. You just basically you maintain a pointer to the current top of the memory, and you cut your pieces above that top. It's trivial to allocate, very fast, very efficient. But of course, it's limited in terms of runtime without having to reboot. And if your system has to run longer than this time, then you are forced. You cannot avoid. You have to do something against this. You have to do something for recycling. You have to recycle, and this is basically already, a first step towards garbage collection. And in particular, it means that you have to find a way of at least detecting garbage. There is a lot of objects in the memory, and some of these objects are, like the bottles before, are no longer used, and others are still used, and all of them are basically mixed up in the memory. So you have to find a way how to detect garbage. And you have to be aware, the reason why I'm talking about that is because each object has a life cycle. It starts with allocations, malloc or new or however you want to call it, and then it's in life for a certain while, and then it becomes garbage if it's no longer used. Now the question is now what to do about this. And you should be aware of whatever. If we come to the problem what to do, but whatever you do, and however you collect your garbage, you will, in the end, you will end up with what we call fragmentation. So you end up with some gaps in between the non-garbage objects. And this is bad. First of all, it's bad because it's difficult to identify the gaps, and second, it's of course, it's more and more problematic because even though you would have enough space, if you would sum up all the gaps, to allocate an object like this one here, you cannot allocate it because none of the gaps is big enough. So you would have enough memory to allocate this, but you cannot because the gaps are too small. The small object that fits, in this gap, but the bigger object doesn't fit. So that's the fragmentation problem. Whatever you do, you have to cope with the fragmentation problem. Now again the question what to do, but before we solve the problem, I want to keep the tension a bit up, and I want to put this situation that I was just mentioning, this sort of fragmentation, this sort of heap-like memory. It's also called a heap. This heap-like memory, I would want to put it against another type of memory, which is called a stack memory. And you may know, I mean, hopefully you know after this lecture about compiler construction, you may know that each thread in your system has a stack, a so-called call stack that is used to call methods. That whenever you call a method, then a new stack frame will be allocated on the stack. You see here in the most basic method is P. That's at the bottom. And then P calls Q, then a new frame is opened, a new activation frame for Q, and then Q calls R, then a new activation frame for R is called, and R calls R again recursively, then another activation frame for R is called, and all these activation frames contain what we call the local variables. If you have a method and then local variables in the method, then they are all allocated on the stack. And now the difference between the stack and the heap that we just saw is that the stack doesn't have this fragmentation problem because it's sort of it follows a certain pattern of usage in terms of last in first out. So whatever was last coming in is getting out first. This call R by R, that will finish first, and then it will fall back to the other R, and then the other R will finish, and then it will fall back to Q. So it's kind of a real stack. It's pushed upon each other every activation frame, and then it's popped down again in the reverse direction. So this is a good way of how to use memory without fragmentation. And also, even without having to care about garbage. There is no garbage here at all. And at the moment, I just want to put this aside to the heap way, But a little later in the talk, we will see that in the end there is one opportunity to relieve the problem of garbage collection by intensifying the use of the stack. So I will come back to the stack a little later. Okay, but now we take a slightly different view on what the heap is, And this slightly different view, before we took a low-level view, it's just memory, But in fact, the higher-level view is, of course, there are a lot of objects allocated in the heap, on the heap, And these objects are referring to each other. They're connected with each other. This is why these arrows are included here in the figure. And of course, if you want it or not, whenever you say something like X next becomes Y, then you create such a dependence, you create such a reference by saying that the next, in that case, it's just a fantasy name. Next is a fantasy name. So the next field of object X refers to object Y. So you get a lot of many thousands, hundreds of thousands, millions of such relations, such references, such dependencies, and in the end, you get what's called an object graph. You get an object graph in your memory. And now, looking at this from this higher view, we could start thinking about how to detect garbage. That's our problem of before. Yeah. And of course, one simplistic way of looking at this problem is, yes, you leave the problem to the programmer, as many other things, the programmer is responsible for so many things. Why shouldn't he or she be responsible for detecting garbage, for actually telling the system that now this is garbage? So this would mean that there is a separate explicit operation called, for example, dispose, and then it would go as shown here, For example, if X would dispose Z or Z, then that would mean that Z would become garbage, and would the runtime system would basically inform the garbage collector, now Z is garbage, you can collect it. But the problem is, of course, that there may be references like the one from Y, to Z, that X is unaware of. Why should X be aware of the reference to Z from Y? And what's happening is absolutely catastrophic. What's happening is you have a dangling pointer that basically literally means basically you fall down the wall somehow. If you try to trace this pointer, if Y tries to trace this pointer and to reach Z, then this is catastrophic. So the real question is, who is actually allowed or authorized to call this pose? And this question is very, very, very difficult. And in the end, if you think a long time about the question, then you have to come to the conclusions: no one except the system as a whole. There are some workarounds, I would call them, in particular in the C++ world, where you cannot have a clean garbage collection for reasons that I come to. They are called ownership models, and in ownership models, like if cars, are finally bought by an owner, and then the owner is responsible for the car. To define when this car is becoming garbage, you define a certain owner in the system for each and every object. You can do that, and then you have to rely on your programming that this owner is aware of every of these references that we just saw before, and nothing bad happens. I'm not pursuing along that track in the following, because first of all I don't believe in it, and secondly it's a different story. Okay, but there would be other solutions, like for example reference counting. You could add a reference count in each object, and the count could actually count how many references are leading to this object. And for example, in this example, there would be Y would have a counter of 1, and Z would have a counter of 1, and X would have a counter of 0 in this example. And if you relocate this pointer from to Y, relocate it to Z, by saying x.next becomes Z in this assignment, that's exactly what's represented in pictorial form. Then, of course, there would have to be a daemon behind the scenes who would immediately decrease the count of Y by 1 and increase the reference count of Z by 1. And first of all, that daemon would have to work. That this overhead would be sort of bookkeeping overhead, and secondly, it would have to be quite fast. Because for example, in a multi-threaded system, other threads might interfere. And third, it doesn't solve the cycle problem. If you have a cycle like on the right here, if you have an XYZ cycle on the right, then all the reference counts would be plus, positive all the time, and you wouldn't ever get to garbage here. By the way, of course, it's obvious, but I still should say that, as soon as a count is becoming 0, that means that no pointer is leading to this object at the moment, and then it's becoming garbage. This is a almost obvious inclusion, or implication. If there is no arrow pointing to an object, then it cannot be reached from anywhere, and that means it's not useful anymore, and then it's garbage. So as soon as the counter is falling down to 0, then the object is garbage, and that is garbage detection at its best, with all the buts that I just tried to make here. But the other direction is not valid. There can be garbage without the reference count being 0, like in the circle that I just cycle that I just explained. So it's unfortunately it's not a very good criterion, in particular in the cases where there can be circles. However, I have to say that there are cases that can avoid circles, like so-called modular systems. And the first system is. And Jesus told me that he himself worked with modular 2, in modular 2, for example, there are only DAGs, acyclic graphs, and here, I mean, if you're thinking of objects that contain modular code and modular static data and so on, then global data, then you can easily use reference counting for this specific kind of memory. And actually, that's what we do in the systems that I tried to explain, to make you aware of before. This is an example where, I mean, there are intrinsically no cycles in the system, because all these modular dependencies cannot have cycles. Otherwise, the design is wrong. And if that's the case, then you can use reference counting. So I don't want to put down reference counting at all, but it's restricted, and also it has overhead behind the scenes. So what else? What else? How can you detect garbage collection? Garbage without all that. And if you look closely at this diagram that I already showed before, then you see the areas that are circled in red here, and these areas, as you can see, are sort of detached, from the rest of the graph, and they are of course garbage, because they cannot be reached from any objects outside of their small privacy, and basically that means that they are garbage, And so the alternative to what I already mentioned and what actually fails is to detect garbage sort of ab initio, meaning that you detect garbage by basically starting from some route and tracing all the objects that are reachable from this route, and then finding those who are not as a complementary set. And that's called the garbage collection service. Now, maybe a small story. This is the Dorado workstation, and the Dorado workstation, as you can see, it's not the newest one. It's actually one of the middle of the 80s, and it was a very, very advanced development by Xerox PARC in California. And it was at that time, it was the most advanced computer in the world. It ran a language that still today would be top notch. It was called Cedar, a system that was even better than all the Linuxes and all the Unixes and so on and so forth. So it was a totally great system. It was overwhelmingly great. And I remember this period. It was definitely a highlight in my life. But what happened was that every once in a while, each day, the system was sort of freezing. You worked and typed and did this and did that, and it was multitasking at the time already. But maybe every 2 or 3 hours, suddenly the system froze, and you couldn't do anything, and it froze for more than a minute. And there was nothing to do. You just had to lean back and relax. You couldn't do anything. And of course, I was at the beginning, I was sort of speechless. I mean, what's happening here? And then everybody except me, of course, knew that this is garbage collection. So there was sort of the stop of the world method used. They stopped the entire computer, and then it was doing collection behind the scenes. But you, as a user, couldn't do anything. So that was my very first experience with garbage collection. It was a pain. It was a showstopper. So, to summarize, why garbage collection? There is no natural way of finding ownerships of a model, an ownership model of objects. There also is, you cannot trust in well, you can, but I mean, it's better not to trust in the ability of individual programmers, in particular if the notion of who is allowed to explicitly release an object is so fuzzy, and also, of course, you want something global, as I tried to show with this object heap, that doesn't really need any contracts, memory contracts across APIs. Want to be able to switch from one API to the next without having to mention how the garbage has to be handled by the other API. Okay, so these are a few reasons why you would want garbage collection. And now this after this story, you see the story. Probably you see it on the top. That's really what was happening. The mutator, which is the application, it's called the mutator in the garbage collection terminology. That's actually the application that does some useful things. That was suddenly interrupted by these red periods, GC, meaning garbage collection period, and they were no longer the mutator was no longer allowed to mutate the graph. And that, it's okay, we did the same in the Oberon system, but in Oberon it took less than a second. It was not noticeable, but with the Dorado machine it took more than a minute, and that was just simply unacceptable. So what the one of the potential solutions was, and that's immediately clear, is you do it incrementally. That's shown at the bottom here. You do some mutator stuff, then you do some garbage collection stuff, and then you do some mutator stuff and so on, and you slice up the whole procedure into small slices, and then everything is a little bit delayed, but it's not like, you having to wait a minute or so. That's called incremental garbage collection. We will see that already that, is a big challenge. We will see that in a few minutes, but it's getting even worse, if you want real concurrency. If you're saying, and it would be, logically would be the right thing, to say that garbage collection is just as any other mutator thread is just some thread, some thread running in the system, and doing stuff. And in the case of the garbage collection, the stuff would be to collect garbage, to detect garbage, collect garbage, blah blah blah. But that's not so much different from what all the other applications do. So the ultimate stage, this is actually today, it's a hot research topic. You look at garbage collection as just a concurrent thread as all the others. And one of the goals of the second part, the more advanced part of the talk today, is to show what kind of problems occur if you want to do it. So the question is, the end, the question is how to orchestrate the garbage collection. You need it for reasons that we just saw, and then the question is how to orchestrate. Now let us, before we come to the problems, if you orchestrate it in a more sophisticated way, let us just look in more detail at very simple stop the world, STV meaning stop the world garbage collection. And again, if you do it cleverly and if you do it efficiently, then you can, with today's performance, you can reduce it to below a second per gigabyte. That's a little less than a second per gigabyte. So you can stop the world. With current systems, that is going almost unnoticed by real users. We come to the problems with that. It's not a sustainable solution. It won't scale up, in the future. But at the time, you can do it. And just to get a glimpse of how a garbage collector works in practice, let us assume a simple stop the world garbage collection. And that consists of two phases. The first phase is the mark phase. And this is actually equivalent to garbage detection. So the first phase is actually made for detecting garbage. The second phase is then the actual collection, and it's also called sweep. You sweep through the heap, you sweep through the memory, and collect all that garbage. So it's a two-phase thing. And now the mark phase, and now we're coming back to what I mentioned before. We froze this topic, and now we revive it. What you do is basically think of this object graph again. And there must be some roots, where everything starts. And the question, of course, is what are these roots? We come to it in more detail, but for the moment we just take it as a concept. There are some roots of pointers that you can start the whole machinery at. And you starting at the roots, you have to traverse this this object graph, and what you do, you basically paint all the traversed objects. I mean, metaphorically, you paint them maybe red, and then all the memory that is not painted red is not reachable, because otherwise you would have reached it by traversing the object graph. So all the rest is garbage, right? And in the sweep case, what you do, you somehow, how it will be done, we come to, but you somehow, basically you somehow sweep through that heap and collect all the non-red parts and give them back to the memory manager, basically. And as a side remark, which is, for those of you who will ever come into a situation where a garbage collection has actually to be programmed, as a side remark, you shouldn't do that eagerly. You should do it lazily, in the sense that you don't collect the garbage, you combine it with allocation. That means you delay the collection to the point of time when you need new memory. That means you can actually skip or avoid the sweep phase almost totally. That's what experts actually recommend. So you don't explicitly do the sweep phase, but you combine it with the allocation phase. So you do it. It's called lazy. Okay. Now, what are the root sets? I have to be more explicit now. The root set. First of all, there are what's called in Java, for example, static pointers. All the pointers that are static, all the pointers that are global, they are definitely belonging to the roots. This is where everything starts. That the static part of your design is basically the system part. That's part of the root. But of course, if you remember the call stacks, there may be lots of objects in local variables on the call stacks. And I'm using plural here because there may be many call stacks if you have many threads. In a multi-threaded system, there may be many call stacks. And the call stacks, of course, may also contain pointers, that lead to objects that you should trace, because at the moment the call stack is an active part of the memory, and there may be references from the call stack to the heap, and so you have to trace that as well. But this is not so easy. The global static pointers, they can be, and this is the first contact between compiler and garbage collector. They can be made known to the garbage collector in terms of metadata. It's called metadata. These are some maps. Every object with static pointers has a map associated, and the map shows the garbage collector exactly where, at what offsets in the object the static pointers are. So that's what we call metadata, and the very first and very important task of the compiler is to transfer this metadata to the runtime, to the garbage collector. In the stacks, it's not so easy, because that would mean that you would have to have metadata associated with each method, because each method has its local variable, and you would actually need a map or a metadata part for each of these methods, and it cannot be avoided. In Java, it's almost the only solution. You cannot do it otherwise, but it's already a big overhead, and it's a big addition to, there's a lot of metadata if you have a lot of methods. In the simple collector that we are discussing right now, you could use some heuristics. For example, you could just sweep the whole stack and then basically apply plausibility tests. Can basically, with each, that an address is 4 bytes long, for example, and then you can plausibility test each of these slots. Could it be that this is an address? So is the range of the value of these 4 bytes, is that a plausible value of an address? Yes or no? If no, it cannot be a pointer. If yes, it's probably perhaps a pointer. Then you check, is the alignment correct? For example, if all the objects are aligned to maybe 4-byte alignments, that you only align at 4 bytes or 8 bytes, then you can check the lowest bits, and if the lowest bits are 0, it can be, it can be an object. If the lowest bits are not 0, then it's definitely not an object, because the allocation is saying something different. That's another plausibility test. And then there can be other redundancy marking stuff added to objects themselves that increase the probability that your guess that you make as a sweeper through the stack is correct. Okay, and then what happens? And this is actually important to understand. What happens? So what could happen? The first thing that could happen is that the garbage collector detects something that could be a pointer, and all the plausibility tests succeed. So then the garbage collector must come to the conclusion, okay, this could be a pointer, but it could also be not the pointer. It doesn't know. The garbage collector does not know. And the question is this a problem? The answer is no, not really. Because if the garbage collector, this is called a false positive. If it comes to positive result, but it's not true in the fact because it just happens to be by accident. It looks like a pointer, but it's not. It's an integer value or something. Then it doesn't trace it, and that means if it was if the garbage collector comes to the conclusion that it could be an object, then it traces it, and so it paints it red, and it won't get collected. And it could be false, a false positive could be false, but it wouldn't hurt so much because there would be some garbage, that may not be collected. But that's not a tragedy. The opposite would be a tragedy. If the garbage collector would come to the conclusion that something is not the pointer, and then it would not trace it, and it would be left white, would not be painted red, and it would be collected, but it was not garbage. The compiler was making a false assumption. That would be a catastrophe. So false positive are not a catastrophe, and in a more so-called conservative garbage collector, this is afforded. So there are plausibility tests on the stack, and that's it. And then there is a third source of root set pointers, and they are registers. The third set consists of registers, and this is the hardest part. Of course, it's very difficult to decide if registers now contain references or not, of what the values of the registers are. And for that reason, a good compiler has so-called safe points or safe regions in the code, and it communicates the safe regions to the garbage collection, and the garbage collection can only run at safe points or in safe regions, meaning that maybe there are no pointers in registers, guaranteed. The compiler sort of guarantees, for example, by switching off optimizations and stuff. The compiler guarantees that at this point, at this safe point, there are no roots in registers. Okay, so that's the root set. It basically consists of global static pointers, of pointers in call stacks and in registers. And here is basically the same thing again. And of course, that's only what we just discussed is only the root. Now comes the trace. And if a root is found, then the garbage collector has to trace that root, and then it hopefully arrives at an object, like for example this object to the left here. And the object to the left, of course, has in it again, pointers like the two arrows that lead further to other objects. And again, it's the same story as before. The garbage collector needs to know where these are. And in this case, it's not just, metadata. It's also based on metadata. But because this occurs so frequently, there is a runtime structure called type descriptor. So each object has a type, of course, and each object uses a type tag to point to the type descriptor. And in the type descriptor, there are the offsets belonging to the pointers. And so the garbage collector goes to the type descriptor, finds out about the offsets, and then continues the trace along these offsets. Yeah? And of course, different instances of a class point to the same type descriptor. Here we have two instances pointing to the same type descriptor. Yeah? Okay, but there is a remaining problem. How actually to implement this trace, starting from the root set, tracing the object graph. And the simple solution is just you are using recursion. Basically, it's like tracing a graph, and you recursively arrive at nodes and start and continue. You know, the downside of this procedure is that itself it uses memory. You know, this recursion uses stack memory, of course, called stack memory, and you don't know how much. So it's a little bit dangerous, and you have to be careful if you implement it like that. But it's simple and easy, but it's a bit dangerous. And there are, on the other hand, there are ingenious, really ingenious ways of avoiding that by so-called pointer rotations. I'm not going into that; it's too complicated for the current talk here. But it's an ingenious way of how to do the trace without any additional memory. You know, and I'm not going into it not just because it's too complicated, but also because it's too inefficient. Not recommended. I have to admit we do it in Oberon, and we made actually reasonable experiences with it, but it's for real big systems it's not recommended any longer. So what you need is you have to need an estimation about how big your recursive stack will become, and then you have to reserve enough space for that. But maybe we will remember this option of traversing a graph without any additional memory using this pointer reversion or pointer rotation technology. Okay, and now how to actually recycle? We left open this question before, and I mean the simplest solution of how to recycle is you just link all that unpainted blocks. You know, here the really used blocks are painted in different colors. Before I mentioned just red, but here it's red, green, lila, and black. But all the non-colored parts are garbage, and then basically you just link these garbage parts to what's called a free list. And whenever you need new space, you know, then you traverse the free list, and there are different strategies. You know, you could traverse it, for example, using first fit. So you stop whenever you find a block that just fits. You could use a best fit, so you traverse the entire list and use the best fit, which is actually maybe good for fragmentation. Or you could also use the worst fit, so you choose that leaves most space. So you have different strategies, but in the end you have to traverse this free list, and of course this is not for free, and you cannot predict the time that takes. So in that case, the garbage recycling, which is actually both, I mean, it's the sweep phase and the allocation phase together, is not, I mean, particularly efficient. It's a way of how to do. Another way that's used more often is that you discretize the memory, and you allocate a number of lists, each implementing a certain block size. Here in that case it's actually quite an old solution. Here the block size is 32 bytes, 64 bytes, 96 bytes, and then anything beyond. And if you have that, then you can speed up your recovery or your sweep return recycle phase by already knowing, I mean, which list is the right list. For example, if you have the starting state on the left, you know, and if you want to allocate a block of size 50, what you do is then in that case there is no. I mean, you would use the list 64, you know, but there is no element in that list. So you produce one by cutting such a piece from the upper list and moving it into the 64 list, and then using it for allocating the 50 byte block. Similar system. This is basically just to tell you several options. I'm not going into the details. A similar thing is what's called the buddy system. So basically, you maintain a number of lists, and each block size is double the block size of the next list. And when you allocate new memory, then you first try to find the right list, you know, that actually fulfills 2 to the k minus 1 is equal or is lower than the size, is lower than or equal than 2 to the k. So that's the right fitting list. And if you don't find a block, if that list is empty, then you have two options. You can either go up and split a block of the higher size, or you can go down and merge two blocks of lower size. And you can do both, you know. And that, of course, is a reasonable system, because you are sure, if you're applying this rule, then you're sure that you don't waste more than 50%, because you always go to the right size list, and the worst thing that you can waste is 50% of the block size. And by the way, this is also called internal fragmentation. If you use discretized blocks, it's discrete blocks, and you are not filling them up really with objects, then you waste space. And this is, of course, also not very desirable. Okay, so this is a sample scenario of how you would develop how such a merging would develop. So you would allocate A, then you would allocate B, then you would allocate C, and then you would dispose there would dispose A. That would actually yes, and B would A and B, that would give you free space above, and then you would allocate D, that would lead to the situation next, and then you would dispose D, and you would allocate E, and so on, and on the right, you know, you would actually dispose C, and then you would be at the beginning merging state, and then you can start again. So this shows how you would split and merge, you know, using a body system. Okay, now we're coming to the advanced part of the garbage collection, and of course we have to identify not healed trouble spots, remaining trouble spots. One is, of course, that fragmentation is not healed at all so far. Memory may still leak because we are using a conservative method for the stacks. There can still be some garbage remain forever. The objects have absolutely no control over when they are collected. The objects themselves, they have no idea when they are collected, cannot do anything. And also there is actually only one criterion, which is reasonable, but maybe not the only one. You know, criterion subject is reachable, that means non-garbage. And finally, the most serious problem again is the stop the world pause that imposes unpredictable delays of the mutator. So these are some trouble spots, and now in the remaining 20 minutes or so, 20 minutes, I would like to not discuss, because it's really too much involved in many cases, but just to show you certain ways out of these trouble spots. So a first way out, of course, a strategy would be to not just return the unmarked parts to the collector by, for example, chaining them into a free list, but really to compactify everything. So meaning to move the colored parts, to push them down so that they are contiguous, and all the still free space would be on top. You know? That's called compactifying or compactification by moving. You know? But this has a very serious implication. You know, suddenly, because you move live objects, you move objects still in use, that means that all the references pointing to these objects need to be remapped. This is called remapping. And this is serious, you know, and that has to be basically to be done monolithically, atomically. Because if you don't do it monotonically, then some of the pointers are correct, others are not, and that is the positive implication is that you get again this simple allocation. You just maintain this top pointer and then cut memory. So allocation is extremely simple. But another downside is that you now need precise information about the pointers on the stacks. Because now a false positive would be catastrophic. If you would come to a false positive, I mean, if you would come to a positive that is not true in reality, that would mean that you move something that you better shouldn't, because it's not real object. It's something different. So here you need something called a precise information, and here you need more metadata by the compiler. Here the compiler must really mediate the entire information about how an activation frame is structured. And the registers again, I mean, the registers need to be reliable. I mean, you need to be able to say this register contains a pointer, this doesn't contain a pointer. So you may need a more elaborate save point information system. Here you see a very quick figure about how that works. Before there is the fragmentation, then you collect, and all the green marked objects are garbage, and then you push everything down and adjust the pointers. Yeah. Okay. Next approach to healing some problems is finalizing. You add the option of a finalizer to an object. So you add the option of adding a method. In that case, it's in C#. It's sort of this snake line myObject. It means that this is a finalizer, and then your operating system, your garbage collection system, will call this finalizer immediately before it finally releases and returns the actual object. That's finalization. And here there are a lot of stories, I mean, one sort of obvious way or obvious idea would be to use finalizers to actually nullify all the pointers. And this causes a lot of overhead that really substantially delays the entire system, and is for nothing, because you don't have to nullify, because you do have a garbage collector, you do have a garbage detector. So please don't nullify. It doesn't make any sense. But there are other reasonable uses of finalizers. For example, releasing resources or closing connections, updating statistics, and so on and so forth. This is actually a little bit more elaborate, this system, because there's one reason. On the left you see the same picture as before, but then you see an additional list. It's actually called the finalizer list, and all objects with a finalizer are entered in this list. And if such an object is becoming garbage, what's happening is that the garbage collector finds out, okay, this has a finalization method built in, so it puts it in what's called an f-reachable list, and the f-reachable list is not worked off by the actual garbage collector right now, but it's delayed to being worked off by a separate thread. A separate thread will track the f-reachable list and will call every finalizer one after the other. Now the reason for that is twofold. First of all, you don't delay the garbage collection by outsourcing the task of working off the finalizer list. And secondly, if there is an error in a finalizer method, could be because the finalizer methods are user-made, then it's not the garbage collector that crashes. It goes on to the account of that other thread. But it's pretty complicated systems, and there can be pretty weird situations. Actually, when what's happening, actually, the f-reachable list is that your object that is basically dead, it's resurrected somehow, it's revived somehow. And then it's not allowed to do a lot, because it's basically dead, but it doesn't know. It does know, but it maybe it doesn't respect that it is dead. And that's a bad thing, It should respect I am dead. I can only do finalizing stuff, and I cannot, for example, adding new pointers to me and stuff. It's a critical topic. A third topic is the weakening pointers, or weak pointers, which is a method to have data structures still being collected even if there are pointers. And this happens all the time. For example, if you think of type fonts, the type font files are typically very big, and you need an internalization structure. If your editor system uses type fonts, so you need a list or something of all the containing all the fonts that are currently loaded. But in a way, this list is not really used all the time. It can be as well recreated anew. If you want to get rid of a lot of storage, then you can do that, and then later recreating that. And for that reason, there is this idea of weak pointers that allow you to still connect all these objects, but to tell the garbage collector, look, if there are only weak pointers and no strong pointers, then you can still collect it. In the case here, you see there are only weak pointers, dotted pointers to the left hand object, the green one. Then there is a weak pointer plus a strong pointer to the used object, the red one, and again only a weak pointer to the green one. And that means the two green ones can really be collected because only weak pointers lead to them, while the red one must not be collected because a real pointer points to it as well, and that means it's not garbage. And the implementation of weak pointers is showed on the right hand side here in the slide. It basically is based on another list, another table containing all the weak references. And all the weak references have to pass this table somehow, and that gives the garbage collector the information that is needed. And a very important way out of many dilemmas is generational collection. There is basically a heuristic saying that objects that have been created quite recently, so meaning young objects, are dying soon. It's a sad story, but it's true. So die young is the motto here. And this is particularly true for local objects, and that is the reason why many garbage collectors distinguish between new objects, young objects, and old objects. And for the new objects, you can spend any effort that you want. I mean, the new objects, the heap of the new objects is no longer so big, and the old objects you can neglect. You can neglect in the sense that you don't optimize, you don't collect as frequently, and so on. You use what's called a generational filter. You distinguish between the two generations, or even more than two generations. And then, of course, the critical question is at what moment should a young object be promoted to an older generation? This is a critical question. If you do it too early, then you lose efficiency. If you do it too late, then it's it compromises efficiency. If you do it too late, it also compromises efficiency, but the young generation gets too big. And I should make a personal statement here. I mean, I'm all in favor of languages like Java and so on, but I have to say that Java are not very good in stack mechanisms, and I suspect, but it's not proved yet, and the people haven't really approved this statement, but I'm pretty sure that a lot of these objects that are part of the young generation are actually objects on the stack, and because the stack is not really worked well and elaborated well in Java, they as a way out, they allocate these objects on the heap, and then they use the young generations for these objects. Not only for these, but a large part. And if they would use the stack in a better way, that's my personal claim, then they could maybe even avoid the young generation. It's my personal claim. Okay, that's the generational idea here. So we have 3 generations here. And there's actually only one thing to say, and the important thing to say here is that suddenly the root set is, of course, to be extended. If you're looking at the root set, for example, for the young generation, G0 here, that's the young generation, then the root set is as before. I mean, it's all the roots that we discussed before, plus all the roots coming from generation 1 and generation 2 objects. These are suddenly becoming roots because they are not not traced again yet now, you know. So we have to extend the root set and by something that is called the remember set, you know. And this is actually a task of its own. I mean, how to come to the remember set, how to maintain the remember set. And there are different options here. You can what's called do card marking, or you can put up barriers that intercept each store of a pointer into an old generation object and remember that, you know, somehow. So there is a lot of opportunities, but all of them are rather inefficient and complicated. So that is a real showstopper actually for these generational garbage collectors to be able to extend the root set by pointers in the lower generation. Okay, now a few words about the incremental collection. And there is one subtlety that I can basically explain in 2 minutes. You know, if you look at this figure here, then you see on the top you see a timeline, and basically you see two things. You see on the top you see a thread 1, T1, doing some stuff, and on the bottom you see a garbage collector GC doing actually the collection. And doing the collection meaning marking the objects. And now what does it do? So concentrate on the leftmost graph. You know, it starts at the root. It marks the root. Then it marks the left son of the root. Then it marks the right son of the root. Now, if that interferes so badly with the thread 1, and the thread 1 basically reconnects. You know, that the thread 1 does. Originally, it looks like this. You know, it looks like this, and here we have this pointer. Now here, this pointer is relocated to object. Yeah, no, sorry. We have this pointer here pointing to object C, and now suddenly this pointer here is relocated to object C, and later. And later to object A. And the bad thing that happens here is that object A has been marked already, you know, and the garbage collector doesn't check again. But now there is a new pointer set from object A to object Z, and that pointer it didn't exist here in the middle of this scenario. You know, there was no pointer from when the garbage collector was at A. There was no pointer from A to C. And so the garbage collector stopped at A. But now suddenly, in the meantime, there is a pointer from A to C, you know, and there is no other pointer to C. So the garbage collector has no chance to detect this arrow, this reference. And so C is collected even though it's not a piece of garbage, you know. This is sort of an unfortunate combination of an interference between the actual mutator T1 and the garbage collector in this incremental way. You know, if the garbage collector is stopped and then comes a little of mutator and then comes a little of garbage collector again and so on, you remember the incremental way of orchestrating. In that case, things like that can happen. And for that purpose, we are using what's called the three-color abstraction. And I have to speed up a little bit, so I'm not going into too many details, but what I want to say is the three colors mean black means passed already, traced already. Gray means just about to be traced, on the wavefront. And white means in front of the wavefront, not yet traced. Yeah. And what the situation that we discussed before basically is that suddenly there is a pointer from a black to a white object, not passing a gray one, and that must not be. You know? That must not be. So we have to intercept pointer allocations from black to white objects, because black means traced already, and black to white means that the garbage collector has no chance to find the white object, and it looks at it as garbage. And this, of course, is a very critical thing. There are different strategies, Dijkstra strategies, Steely strategies, where you mark newly created objects gray, or you mark objects gray that just have a pointer assigned to a white object, and so on. You could either mark, if you have such a situation, black to white, you can either mark the target object gray. That means that you have the garbage collector has to pass it again, or you can mark the source object gray. And in both cases, you have a pointer from either black to gray or from black to white, but you avoid a pointer from black to white. And that you are done, basically. Okay, and finally, it's kind of the climax of the entire story here is what's called a copying collector. A copying collector is a collector that does basically, it's actually a simple idea. A copying collector traverses the graph and copies it immediately. So in the case here shown here, it traverses object A, copies it to this other half space. So we are having two half spaces here, a from space and a to space. So the entire from space is copied into the entire to space. And basically you do a breadth first traversal, and you immediately copy every object into the to space. And again, you have to remap all the pointers just immediately, But this is a bit simpler than before because now you do it object by object, so you can do it's sort of finer grained, in a way. So you can it's more efficient, to remap the pointers. Before you have to. You don't have to. It's no longer a monolithic case at large. It's maybe a monolithic case in the details here on the level of a single object, but not in large. So this is an advantage. It's sort of finer grained than just compactifying. It's finer grained, but it's also more memory consuming because you basically need twice the memory. You need the from space and the to space, and basically in the worst case you need a to consider the worst case, which is you need to be able to allocate the entire life set in the to space. So you waste memory here, and this shows it in detail. I mean, scene 0 to 1 to 2, how that works in detail. From 2 to 3, and in the end, in position 4, I mean, the entire object graph is nicely linearized and allocated in the to space. But of course, you have here again, you have an inconsistency problem, because once you move an object, suddenly the old pointers are no longer valid, and you either need another daemon, a read barrier daemon, that intercepts all the reads to objects that have already been moved, or a write daemon that intercepts to all the objects that are written to, again to avoid inconsistencies. An alternative solution that is sometimes used is double indirection. It's a forwarding pointer. In the old, you don't directly follow the pointer, but you follow the pointer, and then you have another pointer. It's twice indirection thing. And in the old system, in the from space, you basically let each pointer in the object point to itself. So you come to the object, and then you circle in the object itself. But as soon as this object is moved, you forward this pointer to the copied object, and then whenever an old object refers the newly copied object, it goes to the old object first, and then through this forwarding pointer it goes to the new object, and the consistency is guaranteed. But here you need to sacrifice an additional pointer per object and an additional indirection per access, which is again in the end it's again a penalty. It's an efficiency penalty. Okay, and then there are solutions like the treadmill, Baker's treadmill, that are basically exactly working as I explained, but in a symbolic way. Here it's not really the actual memory blocks are not really moved, but they are linked together, and they're only re-linked. The difference is that moving is also moving a block from one from the from space to the to space is also a very time-consuming thing that you want to avoid. And the difference between what I just explained to what this copying collector to the treadmill is basically that here you don't do the copy, you actually just re-link the blocks. This is more efficient, but it has other disadvantages. That you don't really get localization. For example, in terms of cache, it's not a good solution. I mean, processor caches. It's not a really local operation here. Okay, that's basically the same. New allocations. You can be pessimistic and allocate them. You allocate them here in the free space, but you can allocate them here or here. And if you allocate them on the top, then you paint them black and you think they are living long. They are already traversed. If you allocate them to the right, then you paint them white and hope they will disappear soon. So allocation can actually be done at both ends of this free space section. Okay. Yes. Now I'm not going into this last topic, which is a very important research topic. And in the end, even if now we know, variations of mark and sweep, like mark and copy, like mark and compact, like copy, and so on. But all these methods don't solve the problem of not being able to give real-time guarantees. In a real-time system, you need to give real-time guarantees. You cannot afford a garbage collector that delays, spoils your real-time guarantees. And this is a very hot topic today because all the systems, there is no longer here are non-real-time systems, here are real-time systems. It's all mixed, all, for example, music and video applications on a PC are real-time systems. So a system is everything, and you need to be able to basically separate real-time threats from non-real-time threats. And this is a very complicated, very intricate stuff. What we did is basically, what everybody else does basically, is you install a separate real-time heap with some constraints, And in particular, there is no way of a real-time object being allowed to point into a non-real-time object, for example. So there are just some rules to be followed, programming rules to be followed and stuff, but in the end, you basically isolate the entire real-time part by adding a new heap for just real-time purposes. And in that yellow marked heap, you restrict the possible operation. You don't garbage collect at all there. What you do there is, for example, you employ self-managed pools. If you have a certain type of object, then you can afford to use a certain pool, for example, a ring or a list of objects of this type, and then you pre-allocate all these objects in the list, enough of these objects in the list, and then you just take the object from that list. That's what I call a self-managed pool. Now to finish up, takes 3 more minutes. To finish up is basically a few considerations relating performance. What are the runtimes? In mark and compact, of course, it's the maximum size of the live set. The size of the heap is not relevant. The size of the live set is relevant. In a copy case, it's again the size of the live set is relevant. In a mark and sweep case, because you have to sweep, and the effort to sweep is of course proportional to the size of the heap. So this is your showstopper for sweep, that's proportional to the heap size. And that doesn't scale, to modern system with a big heap. Another observation is that the CPU load for garbage collection is proportional somehow to the heap size divided by the size of live set. That means that the more empty memory you have, the better you are off, the less performance you have to spend for garbage collection. This is a kind of a thumb rule in a way. So now, why care? First of all, while the garbage collector is not the part of the compiler, it is very tightly coupled. It needs information about layouts of objects, of modules, of static data, and so on in terms of metadata. It depends on save points or save regions. Second, the garbage collector is an extremely subtle thing that needs to be designed and developed basically together with the compiler. You cannot give the task of developing a compiler to one guy and the task of developing the garbage collector to another guy. It's doomed to fail. Garbage collector is absolutely indispensable. With all what we have said, there was no way around the garbage collector. If you want that 24-hour, 7 days a week system that runs all the time, you have to collect the garbage, otherwise you will crash. And last but not least, the garbage collector is a truly fascinating and really active research topic with a lot of unsolved challenges. And what are the unsolved challenges? You have to be aware that applications are getting larger and larger, and memory in particular is getting larger and larger. And unfortunately, it looks like applications cannot cope. Applications cannot make reasonable use of these huge memory. A heuristic study says that an application stops at the use of about 1 gigabyte of memory. And that means the applications compared to the memory that grows and grows and grows every 2 years, doubles basically according to Moore's law, they are becoming tinier, smaller and smaller, compared to, and this is bad, somehow, because you should make the compiler, the garbage collector should, memory manager, I want to say, should make better use of the memory, and should not keep it restricted to 1 gigabyte sort of artificially. But that means, of course, that the garbage collector has to scale up. You need to develop garbage collectors that scale in terms of heap size. And again, the second important challenge is, of course, I think that's actually the most difficult challenge, is to integrate garbage collection smoothly with real-time. To allow real-time threads to be programmed on the same level of abstraction without compromising the real-time guarantees, because otherwise it's just simply of no use. Yeah, I think that's it. Thank you very much.
First, I want to thank you. Part of your presentation is
excellent.
my students.
Okay, excellent.
I teach about design
Yeah.
how you must
Yeah.
problems.
Thank you. It's a smart workaround. Instead of solving the real problem, which is unfortunately strong typing. You need type descriptors. You need to be able to actually, that's what typing is good for. You know of what type a certain thing is. The structure and so on and so forth. But you have to be strict. And I would say it's smart pointers are a smart workaround about the problem, and maybe it's the best effort thing you can do. But I wouldn't sell it as a clean solution from the ground up. To give a quick answer. But I don't want to put that down, It's a super challenge, but I mean, to put it bluntly, I wouldn't use C++, you know. But if you are obliged or if you are forced to use C++, then this is a big idea, a good idea, and a big help, you know, if you have smart pointers. No, but look, I mean, the whole idea of garbage collection is to take this burden away from the programmer. That's the basic idea. To delegate the task of managing the heap, the object heap, delegate to the system. And of course, if you cannot do that, and I don't see any way, I mean, I'm not a C++ expert, but I don't see any way how you could do that in C++. So you must change your strategy towards something like smart pointers. No problem, you know, but I personally wouldn't sell it as, you know, it's kind of a compromise. Yeah. Other questions? Yes, please. Yeah. 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 Well, you cannot do anything. I mean, every system can fill up, you know, and because all the resources are limited, and in the end, if every you're talking about the case where every element on the stack is a pointer, or considered to be a pointer. Yeah. 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 No, you have the danger of not collecting things. Yes. Sure. No. 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 No, that would be catastrophic, you know. The first thing is just suboptimal, and it could really spoil your day, you know. If you in fact you treat it as a pointer, and it would free you block a lot of memory because you think this is a pointer for some reason, but you could free that memory because it's not the pointer in reality. That spoils your day, but it's not. It doesn't lead to a faulty system. However, the opposite, if you free an object which is not garbage, that is disastrous. Yeah, yeah. But this is, I mean, what this sweep mark thing here on the stack, you know, this is what we call conservative marking. You know, this is actually avoiding the disaster. You know, because there is no false negatives. Yeah. Cannot be false negatives. Other questions? Excuse me? You mean this problem, the stack problem, or general? No. 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 Well, I mean, no. The answer is no. Maybe it would need, I mean, it's a little bit like in general physics, you know, where people try to come up with a grand unified theory, you know, and they try, and they patch the old theory and add some new stuff and so on. But in the end, what would really be needed is a new theory, something new, you know. And, well, I mean, the answer is maybe half no, not so strict no, you know. I mean, for example, I could imagine, you know, that you would, I think I have even a very last slide about this, you would, yeah, you see, I mean, you would probably design a suitable piece of hardware, you know. So. What? Yeah. 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 Or you do what I told about in the beginning, you know, you develop application aware garbage collectors that are more aware of garbage, more statically aware. Yes, but design suitable hardware is definitely an option. But I wouldn't be able to tell you how, you know, exactly. Other question? Yeah, 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 yeah. Uh, eh, yeah, it's an interesting question, of course, but you know, it's basically if the compiler does not optimize anything, then after almost each statement that you write as a programmer, there is a save point because the registers are not really used across statements and stuff. You know, then you can be on the safe side, and you could just switch off all optimization stuff. I mean keeping stuff in registers and so on, and then you would probably be fine because then the save point would be after every instruction, and you know, it's not only, I mean, if you're talking about this generic problem of how to identify for the compiler how to support save points, you know, it's also, for example, also for multi-threaded programming, it's the same problem, you know, to get to save points, for example, where you don't have to save all floating point registers and stuff like that, you know, and I would say that in any case the notion of a save point depends on the goal. In one case, the goal is garbage collection, and there you have to be aware or have to care that there is no. Basically, I mean, the only criterion is that there must not be pointers in registers, you know. But in the case of multi-threading, you know, this is not so much of a problem. Then there you have other problems, and so save points depend very much on the goal, on the topic, and I don't think that the compiler could sort of invent the generic save point strategy independent of what the save point has to be used for. But I mean the quick answer is just switch off all the optimization stuff. Quick. Yeah. Thanks for listening. Thanks for your patience. Thank you very much.